Welcome to our astronomy lesson on Jovian planets. In our solar system, there are two main types of planets: the smaller rocky terrestrial planets near the Sun and the large gaseous Jovian planets in the outer regions. Today, we'll explore these fascinating gas giants, their formation, evolution, and the unique conditions that exist on them. Jovian planets are the four giant planets in our outer solar system: Jupiter, Saturn, Uranus, and Neptune. These planets are named Jovian because they are Jupiter-like in nature, Jove being another name for Jupiter. They're also commonly called gas giants, though Uranus and Neptune are sometimes more specifically referred to as ice giants. Unlike the terrestrial planets like Earth, these massive worlds are primarily composed of gases rather than solid surfaces, and they're significantly larger in size. Let's explore how these giant planets formed. The formation of Jovian planets begins with the location in the solar nebula. In the early solar system, there was a boundary called the frost line or snow line. Beyond this distance from the Sun, it was cold enough for ices to condense out of the solar nebula. This frost line was crucial for the formation of Jovian planets. While terrestrial planets formed primarily from rock and metal, the Jovian planets formed beyond this frost line, where they could also incorporate ices made of water, methane, and ammonia. The most widely accepted theory for Jovian planet formation is the core accretion model. In this model, the process begins with the formation of a solid core. Once the solid core grows large enough, about 10 times the mass of Earth, it has sufficient gravity to rapidly attract and hold onto hydrogen and helium gas from the surrounding solar nebula. This gas capture process accelerates as the planet grows, leading to a period of runaway growth. The growing planet quickly accumulates a massive gaseous envelope around its solid core. While core accretion is the leading theory, there's an alternative model called the disk instability model. In this theory, a portion of the solar nebula might directly collapse under its own gravity to form a gas giant, potentially without requiring a solid core first. Eventually, this process results in the fully formed Jovian planet structure we see today, a relatively small core surrounded by a massive envelope of hydrogen and helium. After their initial formation, Jovian planets continued to evolve in several ways. First, their rapid growth was a key feature of their evolution. Once the core reached critical mass, gas accretion happened very quickly in just a few 100,000 years. This rapid gas accumulation needed to happen before the solar wind from the young sun could blow away the remaining gas in the solar nebula. Second, an interesting aspect of Jovian planet evolution is planetary migration. Computer models suggest that these massive planets didn't necessarily stay where they formed. Due to gravitational interactions with the protoplanetary disk and with each other, they may have migrated inward or outward from their original positions. Third, as they evolved, Jovian planets captured numerous moons and developed complex ring systems from leftover material. Jupiter and Saturn each have over 80 moons, while Uranus has 27 and Neptune has 14. Saturn's magnificent rings are the most prominent in our solar system, though all four Jovian planets have ring systems of varying sizes and densities. Now, let's examine the conditions on these giant worlds. The structure of Jovian planets is dramatically different from that of terrestrial planets. Unlike Earth, Jovian planets have no solid surface. Instead, they consist primarily of hydrogen and helium gas, with the possibility of small rocky or icy cores deep inside. Their structure consists of several distinct layers. First, there's the visible atmosphere or cloud tops that we can observe from telescopes. Deeper inside Jupiter and Saturn, the enormous pressure is so intense that hydrogen is compressed into a state called metallic hydrogen, where it conducts electricity like a metal. For Uranus and Neptune, which are often called ice giants, the composition is different. They contain higher percentages of water, ammonia, and methane ices mixed with rock, giving them their distinctive blue coloration. The atmospheres of Jovian planets are exceptionally deep and dynamic, characterized by powerful weather systems. Each planet has multiple cloud layers of different compositions. Jupiter and Saturn have clouds of ammonia, ammonium hydrosulfide, and water. Uranus and Neptune have methane clouds that give them their blue color. These planets experience some of the most extreme weather in our solar system. Jupiter's Great Red Spot is a massive storm that has been raging for at least 400 years and is larger than Earth. High-speed winds are another feature of Jovian atmospheres. Neptune has the fastest winds in the solar system, reaching speeds over 1,200 miles per hour or 2,000 kilometers per hour. Saturn has a unique hexagonal storm at its north pole, a bizarre six-sided jet stream that has puzzled scientists since its discovery. Another remarkable feature of Jovian planets is their powerful magnetic fields, particularly Jupiter's, which is the strongest in the solar system. These magnetic fields are generated by rapidly rotating electrically conductive fluid interiors. Jupiter's magnetic field is about 20,000 times stronger than Earth's and extends millions of kilometers into space. Just like Earth, these magnetic fields create auroras at the poles when charged particles from the sun interact with the planet's atmospheres. To put the sheer scale of these worlds into perspective, let's look at a size comparison. Jupiter is so enormous that more than 1,300 Earths could fit inside it. Saturn could contain over 750 Earths, while Uranus and Neptune could each fit about 60 Earths. To summarize what we've learned about Jovian planets, they formed beyond the frost line in the early solar system, where it was cold enough for ices to condense. Beginning with large solid cores, they rapidly accumulated massive atmospheres of hydrogen and helium. Structurally, they consist of gas and liquid layers with possible small cores, lacking any solid surface where a spacecraft could land. Their key features include thick atmospheres with cloud bands and powerful storms, numerous moons and ring systems, and strong magnetic fields. These magnificent worlds continue to captivate astronomers and space agencies, with missions like NASA's Juno probe to Jupiter and the Cassini mission to Saturn providing invaluable data about these fascinating planetary systems. Thank you for joining this exploration of our solar system's Jovian planets.